All right, so continuing with chapter 12 and finishing it up by talking about the moons of Saturn. This is covering our last set of Jovian moons. We talked about all the other moons of interest around the other three Jovian planets. So now Saturn is our last. That we pointed out before, there are 6 icy moons of Saturn, and the 2 that we care about are going to be Enceladus and the one that's not an icy moon, which is the one shown right here. Okay, so we care about one of the icy moons. I know the way I said it, I was going to say 2 of the icy moons, but we care about one of the icy moons and one moon that would not be considered icy, instead gassy. Still terrestrial though. Titan and Enceladus. Okay. So there they are. Okay, so Titan, we briefly started talking about this before. What do we care about for Titan? Namely, its thick atmosphere. This is very unusual. Cannot stress this enough, how unusual it is that Titan has a thick atmosphere. It's not that it completely is unexpected, it's just unique in our solar system. So no other moon has a thick atmosphere. The conditions for thick atmospheres certainly seem possible. It just, as a generalization, it seems kind of easy to lose an atmosphere, right? If that balance gets tipped in any sort of way over the history of a solar system, atmospheres can get lost to space or freeze into the ground. And I think it's fair to say it's hard to get them back, right? So the fact that we have this thick atmosphere on Titan in our solar system is a very great deal of interest to scientists. The nature of the atmosphere is particularly fascinating because it does have clouds and it supports liquid on the surface, not water, but methane and ethane. This is due to the very cold temperatures that these gases can actually form precipitates, can form liquids on the surface of this world. By the way, this density, of course, is the density of the planet itself. Relatively high, fair amount of rock, but definitely more on the icy side. The atmosphere itself has a fairly, high pressure because we have talked about density in the context of atmospheres as well. Although primarily we talk about density for the actual body of the planet or moon or whatever it may be. I was actually just reading about Titan as I was just preparing, notes over the weekend and content, and I came across something that I hadn't realized, that Titan's atmosphere is a little bit denser than Earth's. So it actually is, a really significant atmosphere. And the certainly not breathable and way too cold for humans to be comfortable, but just the fact that it's so dense is fascinating. All right. And so this is, has an open-ended question that we won't answer just at the moment, but speculating on how Titan is similar in size to Mercury, just a little bit bigger, but has a thick atmosphere while Mercury does not. So think about why that might be. All right. I won't say anything right now, so I'll just really leave it for you to think about. So the nature of Titan's atmosphere is a thick photochemical haze that obscures the surface, and that surface is partially covered in liquid. That's, as I said before, liquid, ethane, and methane. So 2 kind of similar hydrogen-based molecules. The atmosphere, as I said, is thick and indeed is a little bit thicker than Earth's. Mostly nitrogen with a little bit of the methane that kind of forms its clouds and its liquid cycle of rain and evaporation. Other hydrocarbons are in the atmosphere as well, which would include ethane. Okay. And I don't know if there's a major disparity between the amount of ethane that's on the surface versus in the atmosphere, because notice that it's not mentioned. Perhaps it tends to not evaporate as readily and then builds up in those lakes watersheds, and so on. I'll put this out there. It's not required information, but I have heard a lot of speculation that the cycle is rather slow because of the low temperature. And what I mean by the cycle, I mean the precipitation. So that, of course, on Earth, we can have, water going up in the clouds and rain coming in a regular, phase of time that's just a few days, right? Although, of course, rainy seasons tend to be positioned, throughout the year. But the actual time delay is insignificant, right? It doesn't take long for water to say evaporate off of a lake or a sea, and then actually form clouds, and those clouds then can actually drop rain somewhere else. But that whole process is really slowed down on Titan, and would takes decades to complete. So the whole thing is just incredibly lethargic because of the low temperatures. So rain at most would occur every 10 Earth years or so. So really slowed down process. This is showing the surface of Titan and showing labyrinths of valleys. It has a very rough terrain, showing lots of uneven rock, icy terrain, because remember, there's lots of ice content throughout the body of the planet. Also showing lakes of those hydrocarbons, that ethane and methane, in the blue, right? So we have regions of lakes up here, and also, on other sections throughout the surface. There's also these major dune features, which show up really as kind of a predominant equatorial feature on the surface. What we know about the surface of Titan is similar to what we know about the surface of Venus, although with even fewer flybys. And just like Venus, with only when one successful landing, although actually Venus there's been more than one successful landing, but I think only at two. But for Titan, it's just been one. And so not a lot of images taken from the surface, and all the images that we take, as I started to say, all have to be taken with radar imaging because we can't see through the planet with visible light. So we can't have those detailed sort of images that we might for a moon like Ganymede or Europa, where we can just see the surface with a flyby space probe in that visible spectrum, which of course is much shorter wavelength and higher resolution. Instead, we're stuck with radar imaging or infrared, in this case, to actually be able to pierce the clouds. All right. This is showing in black and white those labyrinths on Titan, which is just referring to the maze of valleys made by erosion. So erosion being a major feature due to the thick atmosphere, which facilitates, like I said, that precipitation, certainly some amount of wind, and that means that we have constant erasure of those ancient craters, and they just simply wouldn't be there. So this would be another planet where we're not going to see a lot of cratering, because to see a lot of cratering, you have to have a surface that doesn't change over time. Especially because, when we talk about a lot of cratering, we're often talking about that really early cratering, which means you have to have a surface that stayed about the same for 4 billion years. And that would absolutely not be the case for Titan. So looking at some of these actual liquid features, we can see the lakes, so lots of small lakes, as well as some larger ones, and actual clouds that, based off what the scientists know from their imaging, for us, we wouldn't know, but they know that these are in fact clouds. All right. And so looking at the names, we have names after Maori and Norse showing up in the naming conventions here on Titan, which is just quickly worth pointing out because you see that I think I mentioned this briefly in passing before, that as you move out into the Kuiper Belt objects, some of the newly discovered moons, you start to see other mythologies and cultures represented besides just Greek and Roman. Right? This is going back to the nomenclature. So I think I jumped ahead to show you this. If regardless of whether or not I did, I do want to quickly mention that the tidal forces, which we know from the Earth's moon right away, should be our key reference point, and because it's the same phenomenon. So anytime you see tidal forces, remember that it's very important for all the moons throughout the solar system, very important for all the Jovian moons, but we don't have to look far from home to get a good basic understanding of what we mean by tidal forces, literally like the tides we have on Earth. And those tidal forces mean that when you have a big moon that experiences a lot of tidal forces, tidal locking almost is inevitable. Those big moons all become tidally locked, whether it's the case with Earth's moon, tidally locked to our, Earth itself, a small terrestrial planet, or all these other moons that are tidally locked to their gas giants. Okay, and even Enceladus is not a big moon. We're just about to talk about it, but since it's relatively close to Saturn, it's tidally locked. Okay, but in other words, the only moons that aren't tidally locked are going to be the really small ones that are captured that are far out. Okay, so we really have this, case of tidal locking. So what's kind of interesting is that you could think of it as if a moon meets one of two criteria, but not necessarily both, that it's going to be tidally locked, either big or close to a Jovian planet, okay? Or just relatively big and close to a terrestrial planet. So, the bigness comes into factor with Earth's moon. The reason I bring that up is because of these two standouts, Triton and Enceladus. Because of all the moons we've talked about, despite all the variations that we've seen, right? Because we saw one moon that was volcanic and no other ones were. We just saw one moon that had a thick atmosphere and no other moons had that, right? We've talked about subsurface oceans, was seen more common, but certainly some planets have those big ice sheets, or some moons do, and others simply don't, right? So those are all special. But Enceladus and Triton are special in their own way because Enceladus is the only small moon that we've talked about other than Uranus's moons, which we talked about just so we could talk about Uranus. Otherwise there wasn't really much to say. And Triton, which was the only moon we talked about that wasn't close. Okay, so we got the only small moon, Enceladus, and the only non-close moon. I mean, like a really near orbit. And these orbits on Jovian planets are dramatically close, right? They can be because of the gravity. But regardless, these two moons are tidally locked. Why? Because closeness leads to tidal locking, as I said. And being so large, because Triton is like the size of Pluto, quite a large moon, that means that it's tidally locked also. Of course, its tidal locking is in that strange type that Venus is almost tidally locked with the sun, in that it orbits in a retrograde way. Of course, although I guess in Venus's case, it rotates in a retrograde way, but Triton actually orbits around Neptune in the opposite way of everything else, right? Most of the moons and all the planets. This is just going back to Titan and talking about a lander that landed on the surface of Titan. It was a largely unsuccessful mission due to some mistakes in calculations. Actually came down to conversion between the metric and the American system of measurements. So, like feet to meters, essentially. They managed to salvage it just barely. This is talking about how difficult it is to get there. It's like sending a virus from a basketball to a baseball when they are 15 miles apart. So it sure is a shame that it wasn't more successful, especially because it was an avoidable disaster. But it did manage to take a couple of pictures before it failed. Essentially, it landed much harder than it was meant to. Future missions will return to Titan in the future. Moving on to our last moon of interest, Enceladus. It's an icy moon. It looks a lot like Europa. It's much smaller than Europa, but you can really think of it as Europa's little sister, okay? You got Europa, orbits around Jupiter, fairly large, but very noticeable ice sheets covering its surface with that subsurface ocean right underneath those ice sheets. Noticeable amount of currents and energy coming from the water that are actually moving the ice sheets around, causing them to crack and buckle. All of that would apply to Enceladus, right? same sort of look to it, same noticeable features, fissures, cracks, subduction, all happening, definitely implies an active ocean underneath. Except Enceladus is even more active. Its ocean is even more active. There is water vapor escaping through the cracks, actually ejecting out in jets, in plumes, into Enceladus's tiny amount of, continually formed water vapor atmosphere and escaping into space. In other words, that subsurface ocean creates geysers that spray water into space. This was unexpected, both because we don't see that on Europa, at least not anywhere near as energetically, and not as well documented. Furthermore, we didn't even expect Enceladus to have a subsurface ocean because of its small size. And the idea was that it wouldn't be able to support one, it'd be too cold. But obviously, the tidal friction was underestimated. And I think as the discovery in the last 20 years and further documentation of Enceladus has really allowed scientists to reformulate the really prevalence of tidal heating for these types of moons. And we see that. We've already talked about that. A lot of what we said, I think, reflects that new level of understanding. But you could think of it as starting with this sort of breakthrough and unexpected finding. The density of the planet's pretty low. That shouldn't be a big surprise. This planet, although containing definitely a significant amount of rock, is one of those icy moons. Okay, it is not all rock by any means. Here is a animation or sort of a painting, a digital image showing those geysers. So this is kind of what happens on Enceladus. The ocean underneath causes water to erupt, crack through, and shoot up above the surface of the planet, and because the gravity is so low, into space. What could cause this, right? Well, it has to be these long fissures coming up from that subsurface ocean, but to drive such a heat necessary phenomenon, you would need to have something else happening to heat the ocean. It can't just be some sort of ambient heat in the ocean. And so there must be some sort of volcanic activity happening at the bottom of the ocean, which is why scientists who are interested in extraterrestrial life, which is probably most of them, are so interested in Enceladus, because if there are these subsurface vents, these sources of heat and energy, and you have water, then you might have all the ingredients necessary for life, just like we see life at the vents at the bottom of our oceans. Here is an actual image taken by the Cassini space probe, which was a very successful mission that spent a lot of time around Saturn, slingshotting around its moons, and also orbiting the gas giant itself. The Cassini mission came to its end when it crashed into the atmosphere of Saturn, but that was a planned crash rather than an unintended one. But this actual image shows those geysers, which were represented in the artistic image before. So you can see them spraying off into space. Those geysers produce a donut-shaped ring above Saturn's atmosphere. So basically creating another ring. In other words, Saturn's E ring, one of its outermost rings. Here is a image taken by this individual of Enceladus with Saturn's rings in the foreground. Speaking of rings, well, as you probably know at this point, having done the reading and just being up on astronomy details, you know that all the Jovian planets have rings. Most people, of course, don't know this, and they would be shocked if you told them. They think, oh no, Saturn's the only planet that has rings. But all the Jovian planets do. It seems to be a side effect of being a Jovian planet. You always have a ring. It just so happens that Saturns are bright and wide and therefore very visible to us. In contrast, Jupiter has a very faint ring. Uranus has a dark and narrow ring, and Neptune's is also dark and narrow. So they would be visible in the infrared, but not in the visible light. So when we talk about rings, we could look at a great figure like this, which compares all of them, and see that in sheer size, Jupiter's are large, but because they're not visible, they certainly are not as dramatic. Uranus and Neptune's are proportionally smaller, but that's not a surprise because the planets themselves are. In terms of the history, Galileo saw the rings of Saturn back in 1616, but was confused about what they were. Later on, it was thought that we were seeing different shapes at different times. And then finally, it was realized that what we were seeing were rings. And now we can more clearly see them with higher technology. And if the rings are composed of individual objects, then the inner objects should orbit faster than the outer ones. And this can and has been measured. So, of course, they are not one big solid piece. It wouldn't work for them to be a big solid piece because it's necessary for this to happen, right? For things that have significantly different orbital radii to orbit at different periods. We know that, right? We've seen that again and again. If the rings are big, one big solid piece, well, they would experience the greatest amount of friction imaginable. They'd have to be unbelievably strong to somehow hold together and still orbit as one big solid piece, considering how wide they are in a radial sense, right? As a distance from the center of the planet that they're orbiting. So they have to be separate pieces. They have to move at different rates, and that absolutely is the case. And that's what's shown here, by the way. Imagine a particle in the innermost part of Saturn's ring and see that in a certain amount of time, it's moved further, right? So the time gaps, or rather the spatial gaps between the gray dots represent equal time gaps. So we just see that the closer in you are, the faster you're moving, totally consistent with Kepler's third law. Right there, Kepler's third law. The structure of the rings is that they're full of rock and ice. So they have varying size pieces, chunks of those of rock and ice, mostly ice, that vary from, of course, small, just tiny dust shape, just a few microns across, to a few meters, big clumps. The ring material that forms Saturn's rings does vary in color, with lots of blue from that predominant ice, and sections that have more dirt or dust are going to reflect in a more red color. If we look at a moon that's located near the rings, it has the following composition. This moon is Phoebe, a moon of Saturn. So compared to the asteroid belt around the sun, the objects in the planetary rings are generally, well, smaller, okay? Not a big surprise considering that it's just an orbit around a planet instead of an orbit around the entire sun. So, I mean, if you think about asteroids, they're leftover from building the whole solar system. The rings, well, what are they? They're leftovers from something else, and just due to the very nature of scale, it makes sense that they should be smaller. In terms of numbers, the asteroids will tens of meters to 530 kilometers. And then we have that in Saturn's rings, 77 of Saturn's 82 moons have diameters less than 530 kilometers. And a lot of the pieces that make up the rings are even smaller still. The ring material varies. Lots of regions we have pieces that are larger than 2 inches, but we have other regions where the sizes are strictly in a range of 1 to 2 inches, or always less than 2 inches. So we can have lots of very small pieces depending on where we're looking. Although, as I said, there's some sections with big clumps. That's not a uniform feature of the rings. And when we look at the rings, we have these ravioli-shaped moons that exist within the rings. And these moons are, like I said, really inside the ring. So they carve out paths within the rings, and they are sometimes called the shepherd moons because they shepherd that constituent matter of the rings. And so here are 1, 2, 3, 4, 5 of these moons that exist inside of the rings. And their shape is due to the fact that they are coated by bits of ring material. So they end up having this almost UFO, or as the slides describe, ravioli shape, right? So they're just flattened and elongated in a particular way because of how they interact with the ring material. And so we have, for example, Pan here, and we can see, right, that it carves out this path. Due to the gravitational interaction of all that ring dust, all those ring particles, a path is clearly showing up. Okay? So the actual rings of Saturn are very, very flat, considering that they're thousands of kilometers across. Their thickness is just a few meters or 30 feet. And the cause of the gaps in Saturn's rings are going to be from the moons that are at some distance but form a resonance. So that means they have a regular tug on the matter within that section, right? They orbit, say, twice for every one orbit of the dust that is that particular radial distance. Or in the case of two, they're cleared out by a moon that actually is right there in the rings. So in both cases, you can end up with gaps, either from resonance, all right, which we talked about a lot when we talked about the Jovian planets, the big three that are closest to Jupiter, but then also from a different phenomenon, which is more straightforward, which is literally from collisions. The Encke gap cleared out by the moon Pan, as I talked about before, and when we think about moon behavior, we can have this attraction between a moon and some other particle. And so that means that when we have resonance, we can have objects that move away from each other due to simple ratios. So if you look at this moon here, which is, I have to go back to that figure, but it was one of the moons that we didn't cover in detail, one of the icy moons of Saturn. The name escapes me at the moment. So this moon, although it does not orbit within the rings like Pan, it still causes gaps by clearing out distances of objects in resonance with it. So in other words, rocks are not able to orbit in this section because they have a resonant orbit with the moon. And so that means that over time, a gap forms. It's the same reason we have the asteroid belt, although we will not be getting into that notion exactly. All right, so the shepherd moons, as I mentioned, they also are pushing material out of the way. They form the gaps that way. And what are the name for rocks in the ancient solar system that clump together to form planets? We know those are planetismals. We know the term is accretion. All right, so how did the rings form? If all these planetismals formed the planets, what happened to the rings? Well, they happened from some other atismal bodies, objects, but these being moonatismals. So these would have been the building blocks of moons, the very chunks that would have accreted together to form all the moons we've been talking about, from Io to Europa to Enceladus and Titan. But some of them just were not able to coalesce into a moon, but instead, due to gravitational interactions, got too close to that large Jovian planet that they were destined to orbit, and instead were torn apart. Sorry, I saw someone's hand go up. Okay. Yeah, there'll be one in just a minute. I don't know that's why the hand went out. But yeah, Maxwell, we have one in just a couple minutes. Of course, it's not a test, it's a quiz. But I think that's what you meant. Okay. All right. And the last thing that I'll say is that idea of a moon, moonatismal, right? The building block of a moon, in this case, the potential building block of a moon, what caused it to instead become a ring, because this is just the idea I wanted to get to relate rings back to moons and wrap everything up in a nice package, is that, they get torn apart. They get torn apart by tidal forces. Okay, that's where rings come from. Torn apart, building blocks of moons. And that phenomenon is called the Roche limit, and it's the closest distance to a body, planet or star, where a large object can orbit. So, for example, there's no planet closer to the sun than Mercury because it would get torn apart by tidal forces from the sun. And the calculation comes down to being dependent on just the radius of the main body, the density of the main body, and the density of the satellite. So that simply with those ratios, we're able to determine how close an object can get before being torn apart. And because the dependence here is just dependent on the density of the satellite, nothing to do with it's at least in this form, no reliance on the size and the mass of the satellite, although we could re-express density in terms of those variables. But the nice thing about expressing it this way, just in terms of the satellite density, is we can separate between these different compositions of rocky and ice and show that certain types of moons, namely icy moons, are going to be less likely to be torn apart. So are you more likely to find rocky or icy moons close to a planet? Oh, sorry, the other way around. Yeah. The rocky moons are more likely to be torn apart. I said it backwards. The icy moons are more likely to be torn apart, which is why the rocky moons can be found closer. They can survive. And that just comes down to the strength of the bond that holds the rock together, as opposed to the strength of the bond that holds the ice together. This just shows the process of an icy object being the weaker of the two, getting torn apart when it reaches the Roche limit. All right, so that will wrap things up for chapter 12.